JOSHAPRAHAM. We're back with the general chemistry, son. So, I was still confused on. Okay. I do remember the last time I was still wondering on the H2O having ESP3. Could you explain that again? Because the contradicting slash confusing part for me was there was no promotion of electrons. Wait, H has one unhybridized electron, oxygen has oxygen has two unpaired orbitals. So bonds would be 2p1s, yeah. Pure 2p bonding cannot explain this. Does not mean electrons to higher energy, instead 2s plus 3 into 2p, 4 equivalent 2s plus 3 times 2p. I don't get it, that part. Same total energy, just redistributed. Think of it as reshaping electron clouds, not exciting electrons. What? What the fuck are you talking, bro? Oh, come on. Come on now. Don't do this to me, man. Yes, research tomorrow. 15 minutes. Okay, I still didn't get ESP3. This part made it more confusing. So oxygen H2O has tetrahedral. Oh, how? Because there's only 3 atoms involved. we not move forward until this one line makes sense. 2s plus 3 times 2p. 4 equivalent sp2 sp3 orbitals. I'll explain this in 3 layers. Read all 3. Hybridization is not electron jumping. Yeah, hydrogen does doing anything. Orbitals physically smashing together. Real-time process you can see. Okay, hybridization is a mathematical redescription of electron wave function to match observed geometry. So we don't know. Okay. Orbitals are wave functions. This is the key. Orbitals is not a place. It is a wave function that describes where an atom is likely to be. So 2s is a wave function, wave functions. You're allowed to take wave functions and add them together. This is basic wave physics. Waves can combine, new waves can be formed. Hybridization is with literally hybridization literally let me add these waves together in a smarter way so the bonds point in the right directions. Why oxygen specifically need this before hybridization? Pure orbitals, oxygen valence orbitals, one spherical 2s, 3 dumbbell shaped. If O used these directly, bonds would point 90 degrees. One bond would be S-like, another P-like. How is the S-like bond? I don't get it. S is filled up. Why are we bringing in S? H2O has identical OH bonds, bond angle 104, so nature says these orbitals might be reshaped. Nature says, yes, that's the other point. What 2s plus 3 times 2p actually means. It does not mean electrons move into 3p orbitals, extra electrons appear, orbital physically merge. 4 valence orbital wave functions, we re-express them as 4 new wave functions. So again, we are considering the valence orbital than unpaired electrons that are actually forming the bond. Also, I noticed that normal sp3 is having 5 atoms total. With the tetrahedral shape, while H2O has only 3 atoms. So 2 sp3 bonds are gonna be sigma bonds for each, and again 2 pi bonds. Covalent bonding. Electron density was concentrated along the line connecting the nuclei. Bonds were formed by overlap of 2s, overlap of sp, overlap of 2p, overlap of p and sp. Hybridization uses valence orbitals, not unpaired electrons. This is intentional and correct. Hybridization answers this question. What is the best set of orbitals to describe the geometry of an electron density around the atom? hmm So we always start from valence orbitals, not from how many electrons are unpaired. Electrons are placed after the orbitals are determined. Think of it as orbitals as seat, electrons as people. You design the seats first. Yeah, sp3 does not mean 5 atoms. This is key correction. sp3 means 4 electron domains around the central atom. Mm. So oxygen's valence orbital has place for 4 electron pairs, right? Yeah. Okay, 2 lone pairs. Okay, wait. That's where the lone pairs come up. No pi bonds in H2O. What the? What? H2O is just. Oh. Okay. No, I'm sorry. Yeah. Correct facts by. So, 2 lone pairs. That's what I missed. Okay. I understood till the oxygen having 2s and 2p as valence electrons. Oh, valence orbitals with the 2 unpaired in 2p orbital, while H has 1s with 1 unpaired electron. So the oxygen's orbital is rearranged in a way that there's now 3sp, no, 4 sp3 orbitals that can have 8 e minus in total. And could you continue from here? I don't get the hydrogen bonding and the lone pair of oxygen. Oxygen valence orbitals, electrons. After hybridization, 4sp3 orbitals hold 8 electrons max. Now we only answer how those 6 electrons placed and how do H atoms bond. Place oxygen 6 electrons in the 4sp3 orbitals. Electrons fill orbitals singly first, then pair. Hund's rule. Okay. So oxygen for electrons used. Remaining two electrons pair up in two orbitals. We got four electrons, right? Remain to pair up in the orbitals. This matches oxygen, 6 electron. What does hydrogen bond? One unpaired electron, one orbital only, so each hydrogen can form a sigma bond. Bond formation, this is the key. Two unpaired sp3 orbitals in oxygen overlap with. Ah. So the unpaired is what. Ah, okay. So sp2, sp3 s bond, sp3 bond. So this this lone pair electrons are in sp3 hybridized orbital, and the OH bond, is it called sp3 s bond? Each lone pair occupies one sp3 orbital. Mm-hmm. 10 minutes, 15 minutes. Okay, come on. Fast. Crank it up. Hey, sir, set a time for 15 minutes. Overlap of a p and sp orbital. The H2O's overlap of these bonds are called sigma bonds, covalent bonding, multiple bonds. To describe multiple bonds, we have to consider a second type of bond. Okay, this was covalent bond. There's the other one, right? We're still talking about covalent bond. There's ionic bond. Okay. as BeF2. BE. Come on, boy. Where's BE? For 2. Okay. So it's 2s, fully filled 2s orbital. And F9. 2, 2. So, what happens? BE promotes its electron to p orbital. So we got a hybridized orbital of sp that bonds with the 2p sp s spp bond. Sp hybrid orbitals. Ba, 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 ba. Ba, 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 ba. BF3. Now it's different. B5. Oh, that changes. So we got we got we got 1p. Okay, switch it up. 1, 2, 3. We have sp2. Oh ho ho ho, yeah. sp2 f. Okay, I'm starting to get it. sp2 2p, that makes sense. sp3 tetrahedral. Covalent bonding. To describe multiple bonds, we have to consider a second type of bond formed from 2p orbitals. 2p orbitals with electron density concentrated perpendicular to the axis connecting to the nuclei. So we're pi bond is perpendicular to the plane of sigma bonds. Perpendicular to the plane of sigma bonds. I unhybridized to this is sigma bond. So is this the plane? Oh, that's the plane. If that's the plane, that this is parallel. How is it perpendicular? Oh, bro, fucking. I didn't get this statement. Could you explain the plane of sigma bond? So the sigma bond cannot be rotated. I know. How does sigma bond form? I'll look into it. I know these. Comparison of single, double, and triple bond for carbon. Electrostatic potential map. So these are negatives, I believe. Or is that positive? Oh no. These should be positive. The center should be negative. Let me. I need to look into that. Upon combination of n or atomic orbitals, n molecular orbitals are formed. Each H2, two 1s give two molecular orbitals, one bonding sigma orbital, one anti-bonding sigma molecular orbital. Subtraction of 1s. Somebody's on the chat. Kanishk. Hi. Hey yo, what's up, Kanishk? I appreciate you for checking out the stream, dog. You got a camel as your profile. Can you hear me, Kanishk? Kanishk, yeah. I apologize for the latency. YouTube's latency is kinda amazing, you know. Don't hate me. I guess Kanishk left. uh, Covalent bonding, delocalized bonds. What is the plane of sigma bond? Sigma bond forms by head-on overlap of orbitals. If a molecule has some multiple sigma bonds, atoms connected to the sigma bond defines a plane. Example C2H2. Each carbon is sp2. Three sigma bonds around each carbon lie on in one plane. This plane is called a sig. How? Kanishk, I can hear you. Oh shit. You're still here. I appreciate them, bro. I appreciate you for checking out the stream. I'm not using the cameras because, you know, it's pretty dark out here. That's why I don't use the cameras, you know? What are you up to, Kanishk? What made you come to this holy land? The stream. What is the plane of sigma bond? Okay. I still can I get an image plane of sigma bond. Can I get the plane? So we got C2H2. Okay, this is the plane. Uh-huh. How okay, if that's the plane, how is okay, from what I understood, on the sigma bond plane, the pi bond looks more parallel to the plane than perpendicular. Or am I missing something? You're missing out. Geometric point. The confusion is between pi bond, electron cloud, and p orbitals that create it. Let's lock this down precisely. What defines a sigma bond plane? What defines it? I don't know. That flat arrangement is sigma bond plane. Come on, I don't get it. I don't get it. The concept is so simple that I'm too stupid to get it. That sigma bond. Is this the plane or this is the plane? I don't get it. No, 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 no. What's the plane? If this is the plane, this is the pi bond, sigma pi bond. Pi bond is a parallel. What are we saying, bro? What defines a pi bond? The pi bond lies on the plane because the bonded nuclei lie on the plane. Bonded nuclei lie in a plane. That is crazy. How does bonded nuclei lie on a plane? Mm-hmm. Okay, I'm mm-hmm. That flat arrange. Two perpendicular p orbitals overlap sideways. 15 minutes? No, come on. Faster, faster. Come on, come on. Hey Siri, set a time for 10 minutes. Don't listen. Come on, come on, come on, come on. So p orbital axis is perpendicular to the plane. P orbital axis is perpendicular to the plane. Each p orbital has two lobes. One. What? Okay. Let's take a C is the plane cutting through the C's nucleus, or I don't care about the spelling, come on, not right now. Or is the plane separating the C and C. Come on! Come on, GPT. Come on. What are you doing, bro? Come on. The sigma bond plane cuts to the carbon nuclei. Okay, that's that's established. Now, how in the hell is the pi orbital, the pi bond, perpendicular to the plane? That's literally don't make sense. And ethene, yeah. I don't give a shit about these bonds now, right now. All bonded atoms lie in the same plane. I don't know. Is it though? Does it? Do they though? Do they though? I don't know. Okay. So if I understand this, this would be the plane, right? How is this bond? How is that bond? These p orbitals are centered on each carbon nucleus, oriented perpendicular to the. So the p orbitals goes through the carbon nucleus, sticks above and below the plane. Where's the pi bond? The pi bond forms by sideways overlapping of those p orbitals. Electron density is above and below the plane. There is no pi electron density in the plane. Okay, I'm starting to get it. So the sigma bond is the interaction between the positive and negative p orbitals sticking up from the carbon CC and if and if I'm missing it, let me know. Let me see if it's correct, because covalent bonding, delocalized bonds. What a sigma bond actually is CCK. So sigma bond is formed by the into and overlap along the internuclear axis. For a CC bond in ethene, each carbon is sp2 hybridized. When sp2 orbital from each carbon, these two sp2 orbitals point directly at each other. They overlap along the line joining the two nuclei. Mm-hmm. Damn. What the f- That overlap creates a CC sigma bond. What p orbitals taking up do? Each carbon has one unhybridized p orbital. These p orbitals pass through the carbon nucleus, extend above and below the sigma bond plane. These p orbitals overlap side by side. Pi star. Okay, that's no way, gang. We got 82 subs right now. Hell yeah. Hell yeah. W's in the chat. Beep 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 beep. Did I just reach my limit? Mm-hmm. 10 minutes? No, no. Fast, fast. Covalent bonding, delocalized bond. Okay, I kinda understood this part. I'll I'll look into it deeper when I write it on my note. So the next topic is covalent bonding, delocalized bonds. Just a minute, YouTube. I gotta search one thing. Oh no, did I lost it? No. Fuck me. No way, it's on the other side. Yep. Mm-hmm. 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 Okay. Oh shit, I forgot. Was it? Mm-hmm. Mm-hmm. It's looking good. Okay, okay. Mm-hmm. A lot of people stick to the center. Okay. Mm-hmm. Okay. Oh, why would you do that, people? Who removed the question numbers? Stupid. I like this. Okay, I'm gonna stop with the distraction. Just be back. Oh shit. Okay. Okay. What are delocalized bonds? Normally, a single bond or a double bond is localized between two atoms. In a delocalized bond, electrons are spread over three or more atoms, not just two. This often occurs in molecules with conjugated pi system, alternating single and double bond or ions with resonance structure. Electrons are not fixed in one bond; they are shared across multiple atoms. Electrons are not fixed in one. Okay, benzene, ozone, carboxylate. Okay. Molecular orbitals. Antibonding, bonding, nodal plane. So this part is what explains. I was also wondering if it's something I should. If a compound shows, or can I just by seeing With the bonds involved, I could know if also I'm a bit now I'll bit confused on the H2O. Is that something I should memorize, or is it because if I try to I don't the 2s focusing on and yes, the bond says otherwise, but so that means there's no way to come up with the SP3 other than memorizing it, or am I missing some key to Let's break this into two parts. You asked about resonance and H2 hybridization. Recognizing resonance without memorization. You don't need to memorize every compound that shows resonance. Instead, look for the structural patterns. Conjugated system, alternatives, multiple Lewis structures, charge delocalization, negative positive charges spread over multiple atoms. Aromatic ring. So in the exam, if you see these patterns, you can deduce resonance and memorizing each case. Here, the hybridization comes from the number of electron domains, not just the number of bonds. Oxygen has 4 electron domains, 2 bonds plus 2 lone pairs. If you don't need to promote the 2p mathematically mixed to form, count the electron domains around the central atom. Now that gives you the hybridization. In short, resonance, count electron domains. Okay. I don't, so let's say I didn't know O has 2 lone pairs. How about now? Molecular orbitals upon combination. Okay, okay, okay. Hmm. So electron domain means how many uh, orbitals left on the valence uh, orbital. Not valence orbital. How many suborbitals? How many suborbitals left? Mm, 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 mm. I can't stop the feeling. Not exactly. An electron domain isn't just leftover orbitals, it's just a region around the central atom where electrons are likely to be found. That's the valence orbital, right? Molecular orbitals. Dude, I need to figure this one out. Adding two p orbitals along the internuclear axis, covalent bonding. I think this is one of the hardest part. Yep, these are easy. 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 Kinetic energy, oh shit. Kinetic molecular theory of gases, okay. Diffusion properties of solids and liquids. Oh wait, dipole dispersion. Okay, okay. Hydrogen bonding. Hydrogen bonding. Okay. Ion dipole interaction. Viscosity. I never learned that. Surface tension. I never looked into that. Okay, okay, okay. Vapor pressure. Phase diagram. Of course, that's the phase diagram. Redox reaction. I know this. I know this. Yo, we got this. Chemical equilibrium. Oh no. Okay. Late Chandler's principle. We got this, bro. We got this. It's not. It's not ending. Acids and bases. pH scale. Ostwald's law of dilution. Come on. What are these? Coordination chemistry. Okay. Thermodynamics. Okay. Mm-hmm. So, it's 41. I gotta end the stream, right? Yep. Yup. I'ma end the stream. I gotta sleep. I gotta head to work tomorrow. Type sheet, type sheet. And we got assignments, we got exams. We have time. We just need to make sure we use the time. Peace out, YouTube. Peace out, Twitch.